Hey everybody! This short crash course will describe the key aspects of a safety integrity level. We will talk about the inner workings of a SIL study and how it can work together with the HAZOP and LOPA. This tool is used to design an automated safety function to meet a reliability target. Stick with us. Let's start off with what SIL stands for. The term is an acronym for Safety Integrity Level. SIL is used to define the reliability of a safety instrumented function as a way to measure performance. A safety instrumented function is a combination of sensors, logic solver, and final elements which detects hazards and brings the process to a safe state. As an example, you can use a pressure transmitter to detect high pressure in the process and signal a valve to close. This is an automated function that can bring the process to a safe state. It is important to understand that safety integrity level is applied strictly in the context of a safety instrumented function. SIL describes the ability to reduce risk. Safety integrity level of a safety instrumented function defines a reliability range. This reliability range can be expressed as a probability of failure on demand, PFD, or as a risk reduction factor, which is the inverse of the PFD. As you can see from the chart, the higher the safety integrity level, the more reliable. Everyone wants more reliability, but there's a trade-off. A higher safety integrity level also means higher hardware cost and more frequent maintenance. It can also expose a facility to more nuisance trips. Remember, during the design of a process, it is important to set the right safety integrity level for each safety instrumented function. Conducting a high-quality LOPA is crucial. The implementation of using automated controls to reduce risk is defined in the IEC 61508 and IEC 61511 standards. The first standard is used for device manufacturers to design high-integrity components to be used in a safety instrumented function, such as circuit-level diagnostics, software testing, etc., to reduce hidden failures. The second standard is used for process designers and operators to implement a safety instrumented function to achieve a risk reduction factor target, such as hardware redundancy requirements and proof testing intervals. For example, let's say we have a high-pressure shutdown that has a probability of failure on demand of 0.01, or in other words, 1% chance of failure on demand. The high-pressure shutdown meets the requirements of SIL 2. Safety functions that meet this safety integrity level are capable of achieving a risk reduction factor of 100 to 1,000. This is a key concept here. Depending on the specific process, other protection layers in place, and the tolerable frequency of a consequence, an automated function may be safety critical and need to meet a minimum safety integrity level. We claim that our high-pressure shutdown is at least 99% reliable, or in other words, that it has a risk reduction factor of at least 100. As a safety critical function, we want to ensure it can meet SIL 2. How can we systematically make design and operation decisions to meet the safety integrity level we need? We can conduct a SIL study, which is also called a safety integrity level verification in the IEC standards. A SIL study helps make these decisions: the type of device, such as the type of sensors, logic solver, valves, hardware architecture, the level of redundancy, if any. Voting logic, how an action is initiated based on conflicting signals, and the proof test interval, how and when each component within the safety function should be tested. All of these are required to meet the target risk reduction factor, or in other words, the safety integrity level of a safety instrumented function. Let's try an example. In this example from the HAZOP and LOPA crash courses, we have a separator vessel with product coming in as emulsion. This vessel has a pressure control loop and a level control loop. This vessel has a maximum allowable working pressure slightly above the pressure safety valve, set point at 3,400 kPa. What is the worst credible scenario if PV100 were to fail in the closed position? From our LOPA, we found that the vessel can overpressure if PV100 failed closed, and it can result in a single fatality. Our tolerable frequency is 0.01% chance per year. The LOPA concluded that this scenario was 100 times more likely to occur than our tolerable frequency, even with the PSV in place. This is unacceptable. The additional risk reduction factor of 100 is required. To further reduce the likelihood of the vessel overpressuring, we made a recommendation to add a high-pressure shutdown as a safeguard. The high-pressure shutdown is a safety instrumented function, which consists of a sensor, a logic controller, and the final element. Based on the LOPA, we want to make sure the safety instrumented function meets the requirements of SIL 2, which reduces the risk by 100 times. Let's break down the SIL study into 5 steps. Step 1. Break down the safety instrumented function into its components and architecture. Let's take a look. We can break down this SIF into the pressure transmitter, programmable logic controller, and final element. Step 2. To determine the reliability of our safety instrumented function, we need to calculate the PFD of each component. With the simple equation, the probability of failure on demand of each element can be determined. This equation only applies to components under low demand operation with a 1 out of 1 voting logic, which means there is no redundancy. There are other equations for different voting logic, such as 1 out of 2 or 2 out of 3. There are also different equations for safety functions used continuously, which is considered to be high demand operation. To perform the calculation, you will need to understand each variable. The dangerous undetected failure rate is the frequency of a device failing without you knowing about it. It is a hidden failure rate. The dangerous detected failure rate is the frequency of a device failing with diagnostics to alert you of a fault in the system. The proof test interval is how often the device is tested to ensure that it works. The mean time to repair is the time required to repair or replace a device. Let's try it out on the pressure transmitter, which is our sensor element. The pressure transmitter has a dangerous failure rate of 60 hidden failures per 1 million hours of operation. Proof testing depends on operations. This is crucial and requires commitment from operation and maintenance. Let's say the crew performs a proof test every 48 months. This is to ensure the transmitter can produce the alarm signal in a high pressure condition. Since all the variable units need to be consistent, we'll convert 48 months into 35,040 hours. Mean time to repair also depends on operations and maintenance. Let's say it would take the crew 8 hours to repair or replace the transmitter. The pressure transmitter has a dangerous detected failure rate of 15 failures per 1 million hours of operation. Now that we got all the variables, we can calculate the probability of failure on demand of the pressure transmitter, which is 0.010518, or about 1% chance in any given year. Now that we have found how reliable the sensor is, what about the other components? Since we have no redundancy in our safety instrumented function, we can apply the same equation to all other components. After all the calculations are done, we have a list of components and their corresponding probability of failure on demand. Step 3. We need to determine the safety instrumented functions PFD as a whole. How do we integrate them to reflect the entire function? It's simple. For our example, the PFD of the entire safety instrumented function is just the summation of each component PFD. This only applies if there is no redundancy. The probability of failure on demand of the entire safety instrumented function is 0.080376. Step 4. Now that we have calculated the PFD of the safety instrumented function, let's compare it to our target. The probability of failure on demand of this safety instrumented function is around 0.08, which is around an 8% chance of failure. In other words, it has a risk reduction factor of 12.44. Uh-oh, the RRF isn't quite where we need it to be. We needed a risk reduction factor of at least 100. What we currently have does not meet our risk reduction target determined in the LOPA. If we implemented this function, the process would still be 8 times more dangerous than what is acceptable. We need to find a solution to increase the reliability. What can we do? Do you have any ideas? Step 5. If you cannot meet the safety integrity level requirements, which is what we've encountered here, you can consider how to improve the reliability of your safety instrumented function. How can we approach this? Let's take a look at the distribution of failure in our current setup. We want to focus on the weakest element first. Now you can see clearly a picture of the weakest link in this safety function. Our weakest link is the final element. Our valve is contributing 58% of the total failure. Would adding redundant hardware help? What are the cost implications? What about proof testing more frequently? What is the impact to operation? There are many ways to find a solution to this problem. However, just using a SIL certified logic solver alone would not reduce risk. You cannot have a SIL 3 rated facility. Which method is best suited for your company in the long run? I hope you now have a basic understanding of how to systematically look at risk and gain clarity to make optimal decisions. Any questions? Contact us at www.icarus-orm.com. See you next time. Bye-bye. Class dismissed.